Morning to all of you. As you know, now this is the time for the quiz. Let me send you the quiz, and you are given the duration of 10 minutes. After 10 minutes, we shall start the class. Did you get the quiz? Please start it and let me know. Once it is over, just submit it. We shall start our class from 8:10. The second question. Check. Consume multiple answers, you are free to tick a, or more than one options. Okay? So let me start today's class. Let me share my screen first. Can you see my screen? Can you see my screen? Due time is given till 8:25 a.m. so that to give you some buffer time, because whoever are going to submit after that will be penalized. Okay? So for question two, multiple selection. Well, then give it, leave it. Whatever you are thinking, just tick one. If multiple selection is not allowed, then leave it. You will be given full marks. Question. Okay. So now, uh, if you remember, till our last class, we have discussed that value function and how the value that is how VPI is to be determined, and with respect to new information, what is the value for that particular information, and how it varies depending on the situations, depending on different scenarios, everything. We have discussed those things in our last class. Now, what I would like to say that till that much I have discussed with you. Now, in chapter 16, I am not going to discuss anything more with you. These two topics, that is implementation of information gathering of an information gathering agent, and this is an example of a decision theoretic expert system. These two topics you have to study by your own. I don't think there will be any difficulties, but if you still face any difficulties in understanding those topics, you should ask. Okay? But the topics you need to study by your own. From today, I shall start the second part of our of this fractal, that is making complex decisions. So please go through these topics once and let me know whether the things are understandable to you, because this is the decision network drawn here and you need to understand why this decision network is drawn, based on which what are the attributes, how what is the problem against which the decision network is drawn. You may need to understand. Therefore, study it by your own. I hope it will not be difficult for you to understand. If you still face any difficulty, please ask me. Okay. Now let me start today's topic. That is making complex decisions. Now the fact is that whatever we have discussed so far was on taking a single decision. You are given some set of information and you have to decide a single time. Okay, you have to make your decision only on a single time based on those information. Whatever you have studied so far was based on that. That is, you have to take a single decision. Now, in case of making complex decision, why the decision making is complex here? Because in single decision, you need to make sequential decision. That is, in a sequence wise, in there will be multiple number of states. In each state, sequential states, in each state you need to take a decision and you will reach to the next state based on that decision, and that process will repeat sequentially. Therefore, the problem here we are going to address is sequential decision problem. Okay. So this is what we are going to address it. Now, for sequential decision making, let's start with an example. Okay. So let's start with this example. Let let this be an environment. The let it be an environment. Okay. What does environment means? That this is the entire block, that is 3, 4 cross 3. These are different states on which the agent needs to make decision. Why? Let us show it. This is a game. Okay. Let's see. This is the start point and there are 2 exits of the game. This exit is valid when you win. This exit is when you lost the game. Okay, lost the game. So this is for win and loss. There are 2 exits. If the agent, your agent will start from this position, and this is on blockage. Okay, so the agent has to follow the orange blocks only, because this is a blockage, and if the agent hits that block, it will remain in the same state. Okay, so the agent has to find out such a path so that it can exit through +1, that is, it can win. If it exists through -1, it means that the agent is going to lose the game. Okay. Now, as you know, the blocks could be, I'm just assigning the values so that it would be easier for you to denote the location of each block. Okay. So this is a 4x3 world. Now you're starting from here. Now, if you see, say solution is already known to you, this type of environment, if the solution, if you can at least predict the solution, that type of environment is called a deterministic environment. Now, let's say this environment is deterministic. Environment. And the solution, we know that is, solution is, the actions should be up, then right, right, right. And if the agent follows this path, it will definitely win. Okay. So this is the solution that is given. Now, the fact is that these are the intended direction. That is, if the agent stays in, sorry, it would be in reverse order. Yeah, if the agent starts from the state 1, 1, for 1, 1, the intended action, that is the action that is given. Hello? Well, the TS, if you are here, please check question 6 as it is asked, if any you are here. Okay. So now let me discuss it. And you are not, you don't have any need to be worried, because those questions that are wrongly written be given, against those questions you will be assigned full marks. Okay. So now let me discuss it. That is, if you are starting from this position, the intended action is you should go towards up. Now, the probabilities, actually we have assigned some probability. That is, if the agent is following the intended action, the intended effect, which is, does have the probability of 0.8. Okay. Intended does have, the intended action does have the probability of 0. Whereas the direction that is in perpendicular or right angle to the intended one, that is right angle to the intended one, does have the probability 0.1. Now, for the start, if you see, that is for this direction, okay, for this direction, that is up direction, it does have the probability of 0.8, whereas for left or right direction, it does have the probability of 0.1. Now, as we know, if it hits a wall, it will remain in the same state. That is, if the agent goes to the left direction, it will remain in this state, that is 1 state. Okay. Now, the fact is that if the agent follows the intended direction every time, okay, and reaches the state, the winning state, that is 4-3, then the probability of it is 0.8 to the power 5, that is equals to 0.32768. Okay, now this is the probability that the agent will follow the solution path and it will reach to the winning state. Okay, now there is another possibility of reaching the winning state accidentally. How? If the agent follows the path. That is, if you see that there are two paths, one is starting from here, the agent can follow this path, that is this one. If you can see, if the agent is following this path, if this is the path that agent is following, it will definitely reach to a winning state, that is +1. Now, if the agent is following some path and reaching again the winning state accidentally, that path is say this one. So if the agent is following the blue path that is assigned by blue arrows, if the agent is following that blue path, then the agent will also be able to reach +1. Okay, but here you can see, then the path is going to be right, 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 up and up. Okay, so by following this wrong path, the agent is always likely to +1, or the agent is always also likely to go through that. If we talk about problem that is in that is some advanced thing, you first need to understand the concepts with this example, and then only you will be able to map the things. Okay, so now you need to understand the concepts with this example. Okay, So please try to understand it accordingly. If we follow this path, up, yes, right, yes, correct, up, right, yes, right, right, up, right. Now, if you see that with respect to this solution, if this is the solution and this is the path that the agent is following, then the path is mostly perpendicular to the solution, okay, to or stays in the right angle, except the last one. All the actions are perpendicular to that solution or the as a action solution, except the last action. Therefore, the probability of this path accidentally reaching is equivalent to 0.1 to the power 4 into 0.8. Okay. Therefore, the total probability of reaching this reaching start 2 plus 1 is equivalent to is this plus this. Okay. So it becomes something equivalent to 0.3277 like that. Okay. 776 like that. So total probability of reaching the agent from start to plus 1. The third step, third you mean right, right, right. It is not right, it is up. Sorry, I am wrong. Here you need to take the action as up. Taking right, you will reach to that state. Okay. So here I am now. Sorry. So right, right, up, right. This is going to be the solution if it reaches accidentally to plus 1 with wrong path. Okay. So this is the thing. Now, the fact is that here, therefore, what we need to know is that we need to know a transition model. What is the transition model? That is represented by, we have already discussed about transition model, that is represented by this. What does it mean? That is probability of reaching to state S bar from state S upon taking the action A. Okay. So we need to know the model. Here, as we have already seen that we know the model. We know that this is the probabilities. Okay, probability of reaching this state to this state or this state to that state. What is the probability? We know that. Which action? It will, this will be relevant. Okay. So here we know the transition model, and the fact is that the transition model that we are dealing with is Markovian. Do you know what is Markovian? Do you know what does it mean by Markovian? Markovian means that in a Markovian model, what happens that even though you are given with a sequence of events, but your current output should be totally dependent on the output of previous one, just previous one, not anyone before that. For example, you know, well, let me give you a very simple example. Okay. For example, you know that in Rajasthan or at Jodhpur, there could not be two consecutive rainy days. Okay. So a rainy day could not be followed by another rainy day, but a sunny day could be followed by a rainy day. And there could be two consecutive sunny days. Okay. Therefore, if you would like to predict that whether your tomorrow is going to be a rainy day or sunny day, you are going to see that whether today it is a rainy day or sunny day. Okay. Yes, it is Markov chain. So Markovian model means the output or the outcome in the next state is totally dependent only on its previous date, previous state, and not in the history. That is, you don't need to check whether for the entire week how the weather was. Okay, if it is Saturday, you don't need to check from Monday onwards whether it was sunny day or rainy day, and you don't need to keep the history with you. Only what you need to check is whether Saturday is rainy day or sunny day to predict whether Sunday will be a rainy day or sunny day. Okay? It is a first order Markovian model. You are right. If it is a first order Markovian model, and that is why we are dealing with it. We are not taking any further order Markovian model. Okay? You are right, Mr. It is a first order model. Now, the probability of reaching S bar from S uh, does not depends on the history. Okay, as we have already discussed that it is a first order Markovian model. Now, the second thing is that we need to know the utility function of the agent. Okay, so the utility function or the preference agent that needs to be known. Now, utility function depends on upon the sequence of states. That is, in each state, here comes another very important function, very important function, because that function is important here, and that function is very much important when you are going to study reinforcement learning too. Okay. Therefore, that function is called a reward function. What is that? In each state, the agent is going to receive some reward. Okay? That is denoted by in each state, the agent is going to receive some reward, and it is denoted as R of S. Okay, so this is how the reward functions are denoted. Okay, now in the given example, the example that we have shown here, we have actually the reward function should be integer, not necessarily integer, should be a real number, and it could have some positive value. Similarly, it could have some negative values too. Okay. Now, in that given example, the reward function that is assigned here, reward function in each state other than those two exit states that is assigned here is equals to minus 0.04. Okay. So why that negative reward is assigned here? Because we need the agent to reach that exit. We need that agent to reach the exit very quickly as possible. We don't need the agent should go around in that path. That is, it should go here and then go, it should go here, then again comes back from here. We don't want that. We want the agent to reach any of the exit quickly. That's why we have assigned a negative reward. Okay. Now, what we are going to discuss is that Markovian decision process. Markovian decision process. That what does it mean by Markovian decision process? We have already discussed about Markovian or first order Markovian models. Okay. Now we are going to discuss about Markovian decision process. In case of Markovian decision process, and if we are saying that we are going to deal with a Markovian decision process, then there are something that we should know a priori. What are those things? That is, Markovian decision process is a sequential decision problem in fully observable environment and with a Markovian decision problem. So, Markovian decision problems does consume some preliminary things. The first one is Markovian decision process should have some set of states. Since this is a sequential decision making problem, this is the part of sequential decision making problems, so you should be given with a set of states on the MDP models, that is Markovian decision process model. Okay. Now you should also be given with some set of actions. Okay. If you see this example, these are the set of states. Everywhere, this is the set of states. And similarly, you should be given with a set of actions corresponding to each state. Okay? This is the set of actions. And it is generally denoted as action of S in each state, set of actions in each state. That you are going to that should be also provided. And then the third thing, that is a transition model should also be provided. Let's separate out this one. Then comes that transition model. You know how the transition model is mathematically represented, that is P of S bar by S, that is the probability of reaching to state S bar from state S by taking action A. Taking action A. And the last one is a reward function. That is R of S. Okay. So these are the things that should be provided whenever saying that some process is following MDP model or Markovian decision process model. Okay. So is this much clear to you? Is this much clear to you? Then I shall move on to the next phase. Okay. So thank you. If you all clear, then very, very well, very good. So then what we are going to discuss is called a policy. You must be very aware with that term, that is policy. What do you mean by policy? Can anyone please give some definition that what do you understand by some policy? Anyone? Set of rules, the default set of actions that we can do. That is a very good definition. Thank you, Mr. Shashikant. You have provided a very good definitions, and most of you have said that these are set of rules or set of guidelines. Okay, that is actually policy also signifies here. That is, policy is the solution against what should an agent do at any state. That is, if an agent is randomly assigned to some state, it should know what action it should take. Okay? The environment is known to the agent, and the environment is apparently known. Therefore, the policy on each stage, that is, the action that to be taken given any random state, that is called the policy. That is, if you want to write down the definition of the policy, that is, you can write it like that: the solution of what an agent should do given a random state. Okay, so this is what policy is called in decision making system, and policy is generally represented by the symbol pi. Okay, whenever we are going to discuss about policies, we are going to use the symbol pi. Uh, we are going to use the symbol. So this is how the policy is being represented, and pi of S, that is policy in a particular state, policy assigned to a particular state. That is, you can say that pi of S is the action recommended in state S. So this is what is known as policy pi. Now, now the fact is that you also need to determine, you might be providing some random policy. Okay. So it's not just default set, it is all set of actions. Default set. What did you mean by default set, Mr. Ranjan? I can't get. Default set of actions. You can say that it is a default set of actions, but each action should be defined against certain state. If you are given with a number of states, you should have some predetermined policy that which action is to be taken against what state. Okay, every one of us have some policy, and we do actually implement some policy in each of our action in our day-to-day life. Okay, so now what you need to determine is that is quality of the policy. That is, say you are having some policy. Okay, you know that what to do next. If you, for example, let it be that example. Let it be a very common example. That is, for example, you are working in some company, that is, say, X. In company X now, and you are earning a salary that does have the amount of, say, M. Okay, so you are working in a company X and you are earning the salary M. Now your goal is to earn some salary that amount is, say, for example, 2M or 3M. Okay, now you have to decide some policy. Since I am in this state, that is, my state is X, my designation is Y. So I know that I am in the company X with designation Y. I have to take, or I have to have some policy in mind that since I am in X and I do have those state values, that is X and Y, and if I want to reach that amount of salary 2M or 3M, then I have to take some action. Someone speaking, Mr. Sushil, please mute your microphone. Please mute your microphone. Okay. Then the fact is that you should have some predetermined set of actions, and accordingly you are taking the action. For example, you want to reach to the designation Z. Okay, that's why you have decided previously, say 1 year back, you have decided a policy that you should do an intake, and then you will be able to reach to designation Z, and you will be able to earn a salary of amount 2A. Okay, so after having that policy only, you have started to do your intake. Now there are several other issues too. You must have some plans that if you are not able to complete that intake successfully within 2 years, then what will you will do? If you are not able, or if you are able to complete it successfully, but it takes 3 years, then what you will do and how you will act. So everything, or if due to some unpleasant situation, you might have to leave that program meanwhile somewhere. Then what will do? You will do us not in just in the place of job and everything, but in every place or every situation of life, we do have some backup plans. That if we reach in that state, unwillingly or willingly, whatever it will be, what should we do? Those backup plans are the policy. Okay. So now, say you are having some backup plan, but what is the quality of that backup? That you need to determine too. That's why the quality of policy is also very important. And how it is computed in terms of decision network, it is actually the expected utility of all the possible environment history generated by the policy. That is utility of so this is how the quality of the policy is being evaluated. That is, after executing the policy, what is the history? What is the history that you are having, that if someone has executed the policy, if someone has ended up in that state and he has executed and he has taken the action, and if you are also following that, what you are supposed to reach, to which state you are supposed to reach, that you have to have a clear idea about. Okay, so this is why in decision theoretic systems, similarly, the expected utility of this, that is all the possible environment history that is generated by the policy, is being computed. Okay. Now there comes another thing, that is optimal policy. What does optimal policy signifies? That is, it is that policy that yields the highest expected utility. Okay, so you have policy is a set of action, and you also have a set of policy. Okay, for example, if someone, say somebody, loses the job in a few days, he has some backup plans, and that backup plans might not necessarily be a single one, but he could have a set of backup plans. For example, he has the plan to set up a startup by his own. He might have the plan to invest his money to some share markets and somewhere where his money should get double. He might have some backup plans that he will do nothing. He will simply drive a taxi, and whatever his savings he is having will be kept in the bank itself, and he will drive a taxi and he will earn accordingly. All those are the backup plans. Okay. So the backup plans may not necessarily be a single one, but there could be a set of backup plans. But that one that is supposed to give you maximum benefit, that is, there is possibility that if you set after a few days, if you are going to lose your job and you are going to build up a startup, you may gain millions from that startup, you may lose entire of your investment. Okay, both are equally probable, you can't predict. Similarly, if you invest your savings to some share markets, to some share, the risk is still less, but it is still risky. But if you decide that I will not share my as I will not invest my money anywhere with some risk, otherwise I shall play safe. I shall keep everything in my bank account, and I shall drive a taxi and earn some. It is with lowest risk. Okay, so you might have some, and it always depends on your capability. Everyone does not have the same capability over everything. Therefore, you are the best one to decide which is the optimal policy with maximum benefit for you. For every individual, the optimal policy is going to be different. Okay. does optimal policy is the one that also gives highest reward in the Markov process. Optimal policy is the one that gives you the highest expected utility, that provides you the highest expected utility. It does not give you highest reward, because with a policy you can't earn some reward, you can only earn some expected utility. You can expect something from the policy, you can't earn. Okay, so it is actually the policy that yields highest highest expected utility. Okay, and the optimal policy generally is being denoted as pi star. Okay, so this is how the optimal policies are generally denoted. Okay, so this is the general notation of optimal policies. And if an agent is in state S, it should take the action of pi star S. Okay, now let's give let some action example where we should discuss about some example. Okay, so let's go back to this slide and let's try to determine the optimal policy for this. Now, as you know, these are the exits. And you have the reward value of minus 0.04. Now, very interesting thing is that with a reward value of minus 0.04, what you should aim to reach that exit, that is plan quickly. But similarly, you will also look for similarly so this is going to be the policy. Okay, for each state you have some action to be taken. So for this state, if the agent is in this state, it will go towards this, and it will be asked to follow this path. Similarly, if the agent in this state, it will prefer to have a longer path to reach +1 rather than take the shortcut and accidentally reaching to -1. Okay, is it clear? So this is that fact, that is, for example, an agent is in 3-2, it can easily reach to +1 by following simply this path, but it will avoid. Why? Because by being in this state, it can accidentally reach to -1 and it will avoid it. In 3-2, the agent will avoid it and will take a longer path. This is its optimal policy. Okay, so this is how the optimal policy for this with reward value. Here the reward value is this is minus 0.04. Since the reward value is not that much less, therefore it will prefer to have a longer path to reach from here. Now we are going to deal with some very interesting parts. Okay, very interesting parts. Here, here, this is the optimal policy when the reward value is minus 0.04. That I have already shown. Now, the very interesting property is if you even increase the negative or decrease the reward value towards negative direction, and this reward value is minus 0.162. Now, the agent will prefer, because here being any state and staying on that state or taking some longer path is very painful for the agent, because it has to pay a high amount of negative reward. It has to pay high amount of negative reward. That is why it should always look for a quick exit, very quick exit. It could be negative, it could be positive, it does not matter to the agent. What it wants is that it wants to leave that word or leave that image. Okay, so whenever the agent is here, it will exit through, or whenever the agent is here, it will exit through -1. It does not bother about exiting through -1, because if it stays in some state, it is going to receive less reward than losing the game. Okay, that is why the agent is always ready to exit. Does not matter whether it is going to exit with a win or it is going to exit with a loss. Okay, so the agent will always be biased towards exit. Now, if the reward value varies between minus 0.4 to minus 0.08, then what will happen that for this or for that path, agent will look for the shortest path. Unlike this one, the agent will look for the shortest path, no doubt, but it will still look to win, look towards winning that game. If the reward value is even less, even more, that is, reward value varies between minus 0.02 to 0, then the agent will prefer longer path. It will even be able to stay in the same state. It will don't bother much to staying in the same state. You can see that for this path, it can bump its head towards the same state and stay a few times in the same states. In these two states, you can say that it is choosing that policy that it could be able to stay in the same state, but it should not choose any policy that will divert it to exit through -1. Okay, so that is the thing. So it will avoid -1 exit always. Very interesting property is seen when the reward value is greater than 0. Life is very enjoyable for the agent, and it will never go to exit, because the more it will be in each state, the more it will rotate around. You can see that from any exit, the agent will divert it away. Whether it be +1 or it be -1, the agent will always be diverted away from that exit, and it will always try to be in that universe only, because being in this state, it is going to gain more and more rewards, more and more positive rewards. So if you assign some positive reward to each state, this is what is going to happen. It will be a never-ending game, and agent will not be ready to leave that game or to leave that environment. Okay, it will always try to be there in that environment. Therefore, what you can see that the optimal policy varies depending on the amount of reward that you are assigning in the states. Is that clear? Is that clear to you? So this is a very interesting property that we can see. Okay. Now, the fact is that therefore assigning a positive reward is not a uh, mm, very desired thing. Okay. Because then the agents will not be ready to leave the universe at all. Okay, Mr. Pramod. The fact is that how to assign the reward is itself is a big issue, and we can't actually those that the techniques that we are discussing so far are actually the techniques, the underlying techniques of designing some games. Okay, like in case of game designing, people used to follow this type of techniques. People used to follow assigning some reward to some particular state and all those things. But the fact is that the reward value should be dependent on your problem or on your requirement. If you want your agent to reach some exit very quickly, you should assign this value. Okay. If you want your agent to reach the exit, but you also prefer not to lose, then you will follow this path, or you will assign the reward as minus 0.04. Okay, or something like that. If you want your agent, even though if it takes longer value, it should never go through -1, or it should never lose. It may take some time, but it should never lose. Then you should assign some reward within this range. Okay. So, Mr. Naresh, you are going to learn reinforcement learning after having some idea on it. Therefore, you can say that these are the preliminaries of reinforcement learning. Okay. Upon which the idea of reinforcement learning gets developed. Okay. So in the next fractal, you are going to study reinforcement learning, and these concepts are very much required there. Okay. So now, actually, whatever we have discussed so far, all the examples and everything, that is actually we want to have the message that we need to balance risk and reward very carefully. What is the risk that we are ready to take, and accordingly we are going to assign the reward values to the states. Okay, and this is the characteristic of a Markovian decision process. Okay, balancing between risk and reward. Now, next, what we are going to discuss is utilities over time. Now, what does utilities over time means? Utilities over time is that, well, here we are going to discuss about two concepts. There's a finite horizon and infinite horizon. That is, if you say that you are given with some fixed time, whatever you need to do is you need to do within that fixed time, and if the time exists, nothing matters to you. After that given time, nothing matters to you. Okay. For example, in your life, you have decided that whatever you need to do, you have to finish everything within, say, coming 10 years. And after that, nothing matters to you. Okay. So the same way, if you give some fixed time to your agent, that whatever you need to do within that fixed time, and After that, nothing matters to me. There, that is, in mathematically, you can express this idea as, say, you have the utility of that horizon is 0, is a plus is n plus k is equivalent to okay. So these two are going to be equivalent because after n nothing matters. The fixed time is n. N is that fixed time. Therefore, utility for these many samples and these many samples remain the same. Okay. Now, for the same example, for example, your agent is in the state 3, 1. Okay. And you have given some n. You have fixed upon some n values to be, say, your n equals to 3. You have fixed up that n value. Then the optimal policy can't be this. It should only go through upward. Okay? It should only be like that. Because then the number of states are very specific and you may risk your life to go to -1 to reach +1 within the given instant. Since your time is fixed, you will take more risk. Given n equals to 3. Okay. Yes, I am going to discuss the quiz. Just wait for a few minutes. Okay. The quizzes were pretty straightforward today, so it will not take much time. So now it is n equals to 3. Then comes that is, if now you are increasing the value of n, say your n equals to 100, then you won't mind to follow this path because you have sufficient time or you have sufficient values of n to follow a bigger path to with less risk, less amount of risk. Okay, so it also, that is, this when your n is fixed, that is when you have fixed time or you have given some time limit, then that type of um, that thing is called finite horizon. Finite horizon, that is, optimal action in a state may change given the optimal value. That is, here as I have shown for an example, if your a is 3, then your optimal action will go from this to this, that is, from left to optimal action will go to up. But if your n is 100, then your optimal action will remain as left. Therefore, with if a finite horizon, if it is a finite horizon, then with the given value of your finite states, your optimal action may change. Okay. may change. Okay, and therefore the optimal policy for this type of finite horizon is non-stationary, is called non-stationary optimal policy. So here the optimal policies non-stationary. As you have already seen in that example, that how the optimal policy changes depending on the value of n. Okay. Therefore, the optimal policies here are called non-stationary optimal policy. Okay. Now, here, whatever the examples we have discussed so far, the way we have designed the optimal policies and everything, here actually we are dealing with something that is called infinite horizon. That is, the fixed number of states are not given to us. We are free to take those many steps that are required to give uh, to have an exit. Okay. Now that depends on reward and how it varies with reward, that we have already discussed. So, but the thing is that since we are dealing with infinite horizon, the given number of states are not fixed. So that is why we are dealing with infinite horizon. Okay. So here, therefore, we have some fixed optimal policy. Since our deadlines are not fixed, we can say that here no fixed deadlines. Therefore, we have a fixed optimal policy. At least the optimal policy will not change depending on the samples and depending on the upcoming number of upcoming sequences. Okay, so that's why we have the uh, fixed optimal policy, and in this type of MDP models, that is Markovian decision process, MDP is going to have one terminal state. It is infinite, does not mean that you have to go through infinite number of states and it will never end. It means that you can take as many states as required to reach to an exit. Okay, so this is what, and with minimum risk, you can take as many steps as required. So as many steps as required, and MDP should have a one terminal state. Okay. Now there comes another terminology that is called stationary preference. What does stationary preference means? That is, if you are given with two states, state sequences. For example, you are given with two state sequences like S1, S0, S1, like that, and S0 bar, S1 bar, like that. If you are given with these two sequences, and if the starting states, that is S1 is equals to is S0 is equals to S0 bar, then the preference between two states should be equivalent to your preference between S1 should be equivalent to preference between these two states. Okay, that is, for example, now I am giving you another example again. That is, for example, you prefer that it would be better if the sequence of days, like from tomorrow onwards, it will be like a sunny day, then rainy day, then sunny day. Like that, you are thinking like that. From tomorrow onwards, it will be better if we are going to have this sequence of days. Then, if your tomorrow becomes today, that is, from today also, your preference will remain the same. That is, you should prefer the days like sunny day, rainy day, sunny day, like that from today itself too. Okay, so this is called the station. This phenomenon is called the stationary preference. Okay, so let's discuss now the quiz very quickly. Now, the first answer is a set of attributes is termed as mutual utility and dependence when each attribute of utility is independent of the remaining set. Then, what does decision network represent information about all those things? And if you are not allowed to give those multiple choices, multiple options, then you will be given full marks against it. Now, when the decision maker has a choice of action is referred to, it is decision mode. Okay, and here describe utility function and the algorithm for evaluating the decision network that I have already discussed in our last class. If you did not requesting you to please add the option and send a copy to the email address. So that we can have a copy of the quiz. I can't get your request actually. Ms. Priti, I can't get your request, what you are actually requesting. Anyway, here I have already discussed that in the quiz form, what do you need? What do I need to do? Okay, that I shall see. Adoption to send a copy of email address. Okay. Now the fact is that describe the utility function that I have already discussed in my last class. So there is nothing much to say about it. Here, this is going to be the gain. The question is not complete. Anyway, this is going to be the gain profit. That also I have discussed in my last class. In decision network, the rectangle, diamond, and oval refers to as rectangle refers to decision, uh, diamond refers to utility, and oval refers to chance. Okay, this is decision, utility, and chance. This should be the correct answer. Decision, utility, and chance. Decision, utility, and chance. Yes. Now, here draw the curve. This curve also I have discussed in our last lecture, and you were just asked to draw those curves and all those things. Therefore, in today's lecture, actually, we don't have much to discuss about. Question 6. Question 6. This is going to be the correct answer. Okay. So this is going to be the correct answer. Instead of this is going to be the correct answer. Did you get it? Question 6D. Yes, you're right. This is going to be the correct answer. So that's all for today. And I'm just seeing that what is to be done with the quiz and all those things, because there might be something wrong with this quiz form. And anyway, I'm trying to resolve it as soon as possible. just go through those things, and I am going to upload an assignment today itself. You will be given 10 days of time to complete it. Just go through it and try to make it complete and submit it. Okay, there are programmings, there are numericals, and there are some other questions too. So I'm going to upload it today. Just go through it and solve it and submit within the given time limit. Don't exceed that time. Okay, so that's all for today. If you have any query, you can ask me via mail, and in the next class also you can ask me. So that's all for today. Now, see you tomorrow again. Okay, bye.